Hello, hello. Hello, hello. All right, so let's continue here. Um, Next is going to be refraction at the spherical surfaces. That means we are assuming that we're not dealing with mirrors anymore, and the surface um, of basically the surface here, this curved surface, separates two different materials, two different mediums. So let's say here NA represent medium on the left side, where let's say the light is originated, right? Where our object is, and then the medium on the right side. So let's say this is NB, and this can be, let's say, a glass or water or something like, let's say, different material compared to, let's say, the medium A. And one thing we have here is the surface over there can technically be curved or flat. So for example, then either curved or flat, what we can have here is we can have a modified equation for that, spherical mirror equation. So you can see, right, this particular equation over here is a little bit modified because that takes into account the index of refraction of those mediums. So that's why, instead of 1 over s, you have index of refraction of medium A divided by the s, because, the object here, right, is in that medium A. And let's say here image is then in medium B. So, and in this case, right, it doesn't necessarily mean that it's always going to be the case, but let's say, for example, the equation here is taking NB over the S prime as a ratio. On the other side, you have then the difference between index of refraction, NB minus NA, and divided by the radius of the curvature. And then here, magnification equation, one ratio y prime over y stays the same, but the other ratio, the distances, again is a little bit modified to take into account the index of refraction. That means magnification is equal to negative index of refraction of A times S prime over index of refraction B times the object distance. So kind of like modified a little bit. All right, so, and one of the things that we can have here is to basically solve problems where there are, object that is in one medium, and then the image of that can be generated in the another medium, or because the light is now refracting in the other medium, you can technically have basically a real or virtual image depending on what kind of, like, let's say, circumstances you have, right? But the idea here is, if you're looking at, actually, let me, if I go back into this, into this example, you can see, right, that the light that starts from P actually then refracts. You can see, right, it refracts, goes into the, new medium. Does it mean that there is no reflection? No, there is a little of reflection here, right? But starting from this part, we don't care about reflection anymore. That means we say that the refracted light has the most of the light intensity, and the reflected light, it's there. There's always going to be a little bit of reflection, but it's, negligible basically. So we are concentrating on, refraction. So that's why it's a refraction at the spherical surfaces. So, and whenever you then consider refraction, our sign, positive, negative, for the, a side of this, let's say in front or in the back, actually changes. Now what I have here is, the front is actually the negative side, and then the back is it's a positive side. Again, why that's the case? Because remember, we always used in which direction the outgoing light is as a positive side. For the mirrors, the light happened to be going out in the same direction as the front, right? So it was basically, it was completely reflected back. So the front was the positive side because that's the direction in which outgoing light was going. If here you have outgoing light, going into the back, right? Basically going to the other side. So what we do here is then we take back of the mirror, right? Back of this, let's say surface to be the positive side. Okay, that means, for example, then if the P prime is the image position, then the S prime here is the image length or image distance. We take S to be positive because S is the same side as the incoming light. S prime to be positive because it's the same side as the outgoing light, and R to be positive because R is this distance, right? And it's also in the same side as the outgoing light. That means all of those quantities are positive because they're in the positive side of the system, which is in the back, right? That's kind of like the biggest difference here so far for the, and plus, you have a modified equation as well. So it's important to understand that in this type of cases, right? So for the refraction at the spherical surface, you do have the positive side as the back, and then the image distance, radius, focal length, all of those things now positive if the image is located in the back, right? So let's say for those things. All right, so now let's look at this example. So a rod of the previous example, let's see. Oh, I forgot. So this particular example, I don't necessarily have the information. So let's go ahead and kind of skip that. So here we have a skin diver is 2 meters below the surface of a lake. A bird flies overhead 7 meters above the surface of the lake. Okay. So when the bird is directly overhead, how far above the diver does it appear to be? All right, so let's see what we have. So in this case, so let's say we have a refraction, but it's not a spherical surface, it's a flat surface. So what does it mean? Well, remember for the mirrors, right? So when I'm considered the, a flat plane mirror, then the radius was, we can say it's like basically approaches to infinity. So I can say it's, well, it's infinitely long, right? So basically the radius is infinity for a flat surface. That means we have now two mediums. So you have medium 1, which is air, medium 2, which is water. Now, which one is medium A, which one is medium B? We're gonna have to figure out that in a minute. But what I have here is there's boundary line that separates those two mediums is not curved, but flat. That means one thing I can say here is then the radius here is infinitely long. So it's, you can set that to be infinity. Then this equation NA over S plus NB over S prime, which is then NB minus NA over R. So this equation will be modified a little bit, for this particular example, because R is infinity. So if R is infinity, then you're dividing 1 over infinity. That means the right side of the equation is equals to 0. Well, if the right side of the equation equals 0, then what I have here is this, NA over object distance is equals to the negative of the NB over image distance. Okay, that means this equation basically modifies to this. Okay, again, this is for the, a flat surface refraction. Okay, flat surface refraction. Now let's see what we have. We have a skin diver, which is 2 meters below the surface of a lake. I don't know, so let me draw someone like this. Okay. And a bird flies overhead 7 meters above the surface of the lake. Okay. That means, let's say, I don't know, so let's say here's a bird. Okay. 7 meters above. That means this distance here is 7 meters. Okay. Now it says when the bird is directly overhead, how far above the diver does it appear to be? So diver is basically our observer and bird is our object because we want to find the image of the bird, right? So how far above it does it appear to be? That means we want to find the image. That means bird is our object. And 7 meters is then its position. So S is equals to 7 meters. So let's say this is even 7 meters. And then here, what we're saying here, this guy here is 2 meters, right? But this is neither the object or the image, it's just the observer. So we can just say that this distance is just 2 meters. Now, what I have here is the object is in air. That means air in this case and is our medium A. That means index of refraction for A will be 1 because index of refraction basically is NA, right, is where the object is. And our object is in air, so NA equals 1. And NB here is equals to 1.33 because this is for water, if you remember. All right, so then what will happen? Where will be the image of the bird? Well, remember, so we start with this equation, and then we replace R with infinity because we assume that it's a flat surface, right? So basically, it's a lake, and the surface of the lake is flat. So then we end up with this equation. Okay, and what I want to find here is then S prime. That means I can take that equation, rearrange where then S prime is equals to, right? So it's then negative NB over NA, then times object distance. So negative 1.33 divided by 1, that's the ratio of NB over NA, then times object distance, which is 7 meters. All right. So if I calculate, what I'm going to get here is negative 9.3 meters. That means the distance to the image is 9.3 meters, and it's negative means it's in the same side as the object, right? That means it's in front of that surface. Because remember, the idea here is when the light comes in from the bird, it refracts into the water so that the observer can see. Remember, it has to deflect, it has to change the direction toward the normal, right? Because it goes from lower index of refraction to higher index of refraction. That means it bends toward the normal and it reaches the eye of the observer. But what observer would see in this case is if I trace those, those refracted light, so those are the refracted light, right? So if I trace those ones, then they will appear to generate image of the bird somewhere over there, which is then 9.3 meters, right? Basically in front, above the surface of the lake. So that's why it's negative, because outgoing light is here in the water, right? That means outgoing light is in the water. That's the positive side. And negative side is air because it's not the same side as the outgoing light. You can think of it like that. And what I have here is then the bird will appear here, right? It actually will appear even a little bit bigger than its actual size. But the idea here is the negative 9.3 meters tells you that image of this bird will be 9.3 meters above the lake, right? Same side as the object itself. But the question is, how far above the diver does it appear to be? Well, now we have to do that extra calculation because we want to find here then this distance, right? This distance. Well, then that distance is, basically S prime plus, that extra distance, like let's say, I don't know, let's call this, P, why not? So let's call this P. So S prime plus P. So S prime is then 9.3 meters. That P here, it represents just the distance of the diver with respect to the lake, so 2 meters. So 11.3 meters is how much or how far away the bird will appear to be relative to the diver itself, okay? 11.3 meters. And this is kind of similar to, for example, when you look, let's say here's the lake, and let's say you are standing here, and then you're looking at some object inside. So let's say here's an object. So what you have here is this. See let's say the light from here comes in and then bends away. So this one comes in and let's say bends away, right? And then when you trace them, well, this one is not very accurate. Let me try again. So let's say if it goes like this, bends away. So then if you trace them, right? So they will appear that the object is somewhere over here, right? If you kind of, trace them like this. So it seems like the object is actually right somewhere over here. which is, you know, apparent position of the object, right, where the image is. And think like this: if you're in air looking at something inside, you will find that image is closer to the surface than the object, from air into the water, basically. But if you inside water and look up into the air, image will be actually further away than the object, which we see in this, with this case in the bird, right? Bird is 9.3 meters, image of the bird 9.3 meters compared to the object, which is only 7 meters. That means, you know, image is further away from the surface if you're looking at this case. But here, remember, our NA will be water and NB will be air, because the object here is in water. So if you go again from, you know, higher index of refraction to lower index of refraction, the image will be formed closer to the surface. So that's why if you're like, let's say one of those, if you look at like old school movies, right? So when you use spears to catch a fish, right? So you have to take that into account, because when you see the fish, that's not actual position of the fish. Fish is, you know, actually a little bit deeper, right, than what you see, because of this, you know, change, different in index of refractions. All right, so next what we have here are what we call thin lenses. So we're going to talk about lenses because, and this is different from the last few slides, because when you talk about refraction at the spherical surfaces, like, you know, that bird water or the, you know, pike edge and a observer, you know, those are object, you know, let's say, or the image, right, generated in sort of like a different medium where the object is. Here we can assume that image will be still formed in the same medium as the object. It's just one of the things we do here, we use thin lenses to diverge or converge the light into, like, let's say, to generate the image. So what we have here is, you can see, right, there are two types of lenses we're going to consider. Converging lenses, well, these are also known as a convex lenses, and diverging lenses, and these are known as concave lenses. That means you have concave mirror, convex mirror, and then you hear convex lens and concave lens also. Okay, so try to, on the exams, right, try not to confuse those, you know, lenses and mirrors, because one of the things we went over, right, in the previous video was that concave mirror is the interesting one. It has all those different cases. Convex mirror was the simple one. Here we have convex lens is the interesting one, similar to the concave mirror, and the concave lens is the simple one, similar to the convex mirror. So there's a little bit of that. Okay, so in terms of the type of lenses we're using, generally these lenses are glass, acrylic glass, right? So and double convex is the shape that we're going to be using most. So that means double convex means that both sides are curved, compared to, like, let's say, plano convex, where one is flat, the other one is curved, right? Because technically with the lenses you get, you can see, right, if I kind of, you know, do the shape, right? So there are two spheres, okay? So two spheres. So there's a radius 1 and, let's say, radius 2. So there are technically two radiuses. So that means same thing is here. See, there are two, you know, surfaces. One is there, the other one flat. So that means here, this, you know, the flat side has a radius of, you know, infinity, right? Because it's, you know, it's flat, as we talked about. Same thing is here. So you have, let's say, plano concave or double concave, where both of them have the same shape. Okay, so what we're going to do here is mostly we're going to be working with double convex or double concave. So when I say convex, I mean double convex. When I'm going to say concave, I'm going to mean double concave, unless specifically, you know, we're told it's a, you know, plano concave or something like that. Okay. Now, to understand the differences here is, you can see, right, so the one that is converging, again, this is convex, is basically, you can see, right, it's thicker, right? Basically, you can see, right, it's the size, right? So it's kind of like thicker at the center, okay? And concave is on the other way around. It's thinner at the center. So you can kind of like remember the shape from that. So one thing we have here is let's say when you're considering a lens, right? So you can see that those light rays, or 1, 2, let's say 3, 4, they are coming from an object that is in air, okay? And light then goes through this, lens, which is different material. But then we assume that as the light goes through this lens, it's always going to come out into the air again. That means we don't have image generated inside the lens itself. Okay, so at least when you're considering these thin lenses, right? So when you're considering refraction at the spherical surfaces, you can have something like that. But when you're considering thin lenses, then you never have that. That means they're thin enough that light always gonna refract out into the air and generate image in the air. All right, so you can see, right, it has two refracting surfaces. One, let's say here's front, right, and here's back. You can think of like that. And what I have here is that it has two focal points. Remember, it has two radiuses, right? Like I explained in the previous slide. That means now it has two focal points. So let's say here's focal point 1, here's focal point 2. But it has one focal length because f1 and f2 have the same distance from the lens. That means, focal length is the measurement of those focal points relative to the lens, right? And that's why you have one f, right? Lowercase f, but you have f1 and f2, okay, which is two different focal points. Now, what I have here is this. When the light is incident in front, you can see that it then refracts into the back of the lens, okay? That means the back side, if you remember, right, is the same side as the outgoing light. That's why that's a positive side. When front here is the negative side for the, when you consider, let's say, things like, radius and image, position and all those things. So in this case, the back is the positive side, the front is the negative side, okay? Now, this particular example shows how the light is coming from really far away. So let's say this is an example where S position of the object is infinitely far away, okay? And when that's the case, you can see that the light gonna come parallel to the axis, right? So this, again, we call it optic axis, right? Or just axis. And they come parallel. All the light rays are parallel. And then after that, they converge when they go through this convex lens. See that what the convex lens does is, all right, so it hits this here where this is the normal. So it converges like that. Basically, it changes direction. And then it hits the surface like that. So then it again, changes the direction. That means they're kind of going to go like this, change the direction like that, right? And all of them, going to converge at some point over there. If the object is infinitely far away, then all of those lights will converge at the focal point. This basically the focal point in the back of the mirror, in the back of the lens, okay? And what I have here is, that's basically where my image will be, right? So that's my image, like let's say P prime, okay? So I'm saying that P here is at infinitely far away, but P prime is going to be where the focal length is. And one of the things we will see here is the equation that actually we use for the lenses are the same as the one that we use for the mirrors. It's 1 over S plus 1 over S prime equals 1 over F. And you can see, right, if I replace S with infinity, this whole thing is going to 0. And then this going to gives me then S prime is equals to F. That means the image will be formed at the focal point. All right. So, and same way, if you, let's say, put the object at the focal point of the lens, if I put the point object, right, at the focal point, F1, then you can see, right, the light, kind of diverges from here, but when it refracts, it goes parallel to the axis. Second one refracts parallel to the axis. Third one parallel to the axis, parallel to the axis. It means that those are all parallel to the axis. They will never converge. What does it mean? It means image will be formed at infinity, or so we can say that there is no image. Okay, so there is no image in this particular case. Okay, that means this is kind of very similar to the mirror as well, right? So if you put the object in front of the concave mirror, you will see no image. Remember that, right? All right, so again, this F here is, remember, the focal length, right? And in this case, you have focal length that is always going to be positive for convex or a converging lens, right? For convex lens. That means this F here always positive for the convex lens. Okay. How about if you're not doing the point object, but let's say you have object that is finite size? Well, then we get pretty much all those different nice cases that we dealt with let's say, concave mirror. That means you have, depending on the position of the object, you can have a real image that is smaller, a real image that is same size, real image that is bigger, or no image at all, or I can have eventually a virtual image. Okay, that means as I take this object and move it closer and closer to the lens, then I get different, let's say, size object, an image, and eventually might even get a different type of image, like let's say real compared to virtual. But what we do here is graphically, right, is very similar, in a way that the difference is that the light actually refracts to the other side, but we still use very, very similar ray diagrams, right? Those principal rays that we can use. So here you can see, right, this is nothing but the P ray, but instead of reflecting through the focal point, it refracts through the focal point. So you can see, right, it goes parallel to the axis, then refracts to the focal point on the other side, in the back of the lens. And then here's the other one. Which one is this? So, well, technically this one is going through the vertex, right? So the one that goes through the vertex, right, doesn't change direction at all. So it goes all the way because it doesn't reflect back like this, right? So it actually continues going. So it goes all the way through without changing direction. So you can see, right, all you need is those two rays. But, I'm going to show you that there's another one, let's say you can do, which is one that goes through the focal length here, or focal point over there, and then goes parallel. And then you can see the same thing happens in terms of the intersect over there. All right, so this is going to be then object distance, right? This is going to be then image distance. And, focal length here is from the focal point to the lens. And what we have here is, this is, which used to be called mirror equation. Now it's a lens equation. Okay, so equation for the thin lenses. That means you are considering exactly same equation, but in this case, remember, this side here is the positive side. That means if your image here is, in the back of the lens, right? That means the same side as the outgoing light. That means it's going to be a real image, and all the real images, if you remember, are inverted. Okay, Y prime represents the size of the image, Y represents the size of the object. So many things that are similar. Okay, and in this case, so we can pretty much assume that this will be true as long as the position of the object is greater than focal length. So if this is true, you're going to get something like that. Excuse me. All right. So how about diverging lenses? Well, diverging lenses are similar to the convex mirrors. Is that they give you only one type of image. And you can see from this diagram, right? So let's say, again, taking the object to be infinitely far away, the light rays coming parallel. But after they go through the lens, you can see, right, here's ray 1 going like that, ray 2, ray 3, ray 4, ray 5. None of them gonna intersect or converge to a point in the back of the lens, which is the positive side. So what do? We take that refracted lights and we trace them back, right? You can refracted light, we trace them back. As you trace them back, you can see that then they will converge at some point in front of the lens, which was then the negative side, remember. That means if it's a negative side, that means this has to be a virtual image, because also you can see, right, none of the actual outgoing, refracted rays going to that, point of, like let's say F2, right, point where the image is generated. That means what we have here is, because of the image is generated by the, let's say virtual light, right? So we trace them virtually back. because it's in front of the lens, so it's going to be then virtual. And that means S prime here is then negative. Okay, and remember, every virtual image was also upright, right? But in any case, so that's why what we have here is, if you look at in terms of then the focal length for this type of diverging lens, right? Then focal length will also be negative for that. That means S prime is negative and focal length is negative for this type of lens, for the diverging lens. All right, so similar way, right? So you can see that if the light, you can see, right, incident rays converging toward the first focal point of a diverging lens emerge from the lens parallel to the axis. Okay, that means if they're moving such that they all appear to be, right, so here they all, you know, kind of diverging toward that point, but when they come out, they're going to go in parallel. So that means, you know, there will be basically no image, right, located in the back. So, but what we do here is we're going to look at mostly not just point, let's say, sources. We're going to look at sources that, let's say, objects that have size, finite position, right? So that those are a little more interesting ones. So let's kind of like explore then in terms of how we can kind of like use all those equations and things like that. But before that, there's one extra equation that works only with lenses. This equation cannot work with mirrors. It's called lensmaker's equation for thin lenses. That means this equation is, remember that lens equation now 1 over S plus 1 over S prime equals 1 over F. I can use this equation for lens or mirrors. But for thin lenses only, this right side of the equation, 1 over F, can also be calculated different way. So you can see, right, as I mentioned already, you can think of like this double convex, or this, you know, convex, so like a double because it has kind of those two curved surfaces. See, let's say this one can be extended to one sphere, this one extended to another sphere. So you can see, right, this sphere here interacts with light first. So let's take that as R1. And it's in the same side, right? It's in the same side as the outgoing light, right? That's the same side as outgoing light. That means that happens to be then a positive side. So R1 is positive because C1 is on the same side as the outgoing light. And then here we have the second surface, right? Second surface like this with C2. But here R2 is negative because C2 is on the opposite side of the outgoing light because it's in the negative side. So remember, positive side, negative side. And this equation tells you that you can calculate 1 over F from n minus 1. N minus 1 is index of refraction of the, you know, lens itself. Then 1 over R1 minus 1 over R2. So it seems like, okay, 1 over R1 minus 1 over R2. If R1 is equals to R2, you're going to get 0 over there, right? But the thing here is that R1 and R2 always going to have opposite signs. That means things like this. It's 1 over 5. If you do 1 over 5 minus 1 over 5, you're going to get 0. But if R1, which is 5, R2 is negative 5, then you're not going to get 0. Or when R1 is 5, R2 is positive, then again, you're not going to get 0. And that means this quantity in the parentheses never is 0. Because what you have here is, for this type of lens, which is converging convex lens, what you have here is radius is, you know, let's say R1 is positive. What is R1 is positive, R2 is negative. So this is for convex lens. And if you have a concave lens, then R1 is negative and R2 is positive, exactly the opposite. So this is for concave lens, okay? So that's why what you're always gonna get here is a way of calculating 1 over F, right? The focal length from the radius and the index of refraction of the glass, the lens. That means you have different way of calculating, you know, the focal length. All right. So kind of summarize how we can find the image using the graphical method, right? So this principal rays. So you can see, right, you have 1, 2, and 3. 1 is the parallel to the axis, then goes to the focal point on the other side. 2 is going to the vertex without changing direction directly always. And 3 going to the focal point 1 and then going parallel on the other side. And then they converge or intersect at that point, that's Q prime, which is then the tip of the image, which is at P prime. Okay. That means using those 3, you can always find the image for the, let's say, object, given object. Same way with the diverging lens. So what you do here is, this is P1 or ray 1, right? A P ray, which kind of diverges away for the diverging lens. But remember, it has to go to the F2. So but F2 here in this case is in front, right? So kind of like have to trace it back like that. Okay. So then what you have here is then this V ray just does its thing, just goes straight without changing. And then those two always going to be able to use to get the the image. So the third one can also be used, because remember, the third one has to go through the focal point 1. So it kind of moves toward the fourth focal point 1, but then it's going to be bent, so move like that. But you can see, right, in a way we are assuming that it is pointed toward F1, even though it doesn't go to the F1. But then refracted light at 3, then traced back, and again it converges at that point. So you can see, right, what we get here is virtual, and we get smaller, right? We get smaller. Always virtual and smaller. That means what we get here for this particular is a virtual image, smaller image, right? And same orientation as the object. You can see both of them are, upright. That means that particular, let's say upright or inverted, right, is always going to be, true for the, let's say for the virtual image. Virtual image, if you remember, will always be upright, because virtual image always assumed to be, same orientation, right? And assumed to be like, forming from those virtual lights. And it's always going to be upright. But for this particular case, right, if it's a diverging lens, it's going to be smaller. So converging lens can also give you a virtual image. We're going to see that. But converging lens, when it gives you a virtual image, is larger. Just like when the concave mirror gives you a virtual, image, it is, larger, right? That magnifier. So the same thing is here. All right. So let's continue here. Okay. So we have some examples here. So you can see, right, there's so figure below shows an object and its image formed by a thin lens. So what is the focal length of the lens, and what type of lens, converging or diverging, is it? Okay, so let's look at what we have. So here's the object and here's the image. Well, let's see. So where is the image? Well, image is in front of the lens, which is, remember, is the negative side of the lens. What type of image is it? Well, it's a real image. How do we know? It's upright. Okay, it's a virtual image, upright. So what type of lens should we have over here to give us upright virtual image? Because both of the lenses can give us upright virtual image. But as we just talked about, right, the one lens gives you upright virtual smaller image. The other one gives you upright virtual larger image. And the one that gives you smaller upright virtual image is the diverging, right? So it's the diverging lens or concave lens. That means this has to be a concave lens, okay? Now, what we do here is we take position of the object to be, is position from the lens, right, to be 8 centimeters. Position of the image is then 3 centimeters, but because it's a virtual image is negative. We're also given the object height is 6.5 millimeters, right? And we're gonna then use all of those information to find for part A, right, focal length, and for part B, the height of the image. And it says, is it real or virtual? Well, obviously we know that It is virtual because all the virtual images are upright and in front of the mirror, in front of the lens. But let's say for part A, to find the focal length, I can use 1 over s plus 1 over s prime equals 1 over f, or simplify this where f is equals to s times s prime over s plus s prime. So 8 times -3 over 8 minus -3. All right. So that means, I can then do this calculation to find the position or the length of the focal point, right? Or the focal length. So it's going to be -4.80 centimeters. Again, it's negative because it's a diverging concave lens. Diverging concave lens always has negative distance to the image and negative focal length. And that's why, you have to double check that when you're doing the calculations. All right, so part B, what is the height of the image? So here what I can do is, let's say, remember, height of the image, I need y prime over y. So I need y prime. Remember, y prime equals to magnification. Remember, magnification then is -s prime over s. So if I calculate this, -3 over 8, then I will get, so negative cancels out, so I get positive 0.375. That's why you can see, right, smaller upright image. Smaller because it's less than 1, upright because it's positive, the magnification. And then use this equation, right, to solve for the y prime, because y prime is then y times magnification. That means 0.375 times the position of the height of the object, 6.5 millimeters. And when we calculate, remember, we have to expect a smaller one, right? And we do get 2.44 millimeters. All right, so that's then the image height. All right, so another example here. So a double concave lens, that means just a concave lens, right? That has an index of refraction equal to 1.45, has a radii whose magnitudes are equals to 30 centimeters for R1 and 25 centimeters for R2. An object is located 80 centimeters to the left of the lens. Okay, that means sort of like in front of the lens. So find the focal length of the lens, the location of the image, magnification of the image, and is the image real or virtual? Is the image upright or inverted? All right, so let's do all those calculations. What we're given here is, the index of refraction of the lens. So n is equals to 1.45. And I'm given concave lens, okay? Remember, for concave, R1 was negative, R2 was positive. That means R1 here is -30 centimeters. Then R2 here is positive 25 centimeters. Then I'm given then the object here is 80 centimeters in front of the mirror, the lens, sorry. All right, so I can then since I'm not given S prime to calculate using the thin lens equation, but I'm given n R1 R2, I can use the lensmaker's equation when 1 over f is equals to n minus 1 over R1 minus 1 over R2. I can use this equation to calculate. Okay, so that means it's 1.45 minus 1, then 1 over -30 minus 1 over 25 to calculate this. All right, so one of the things we're going to do here is, remember, so let's say this is, when I do this calculation, it's equals to 1 over f. That means I can take this inverse of both sides. So then I have the focal length equals, so whatever I calculate here, then I take the inverse of that at the end. Or don't forget that. So then focal length is going to give me -30 centimeters. Okay. Again, it's negative because it's a concave lens. I should expect negative. Okay. Now, once I have then the focal length, for part B, I can use it to find the image. Image is equal to then S times F over S minus F. So then 80 times negative 30 over 80 minus negative 30. And that's going to give me negative 22 centimeters. Again, I should expect negative because it's a concave lens. All right. So let's look at then magnification is equals to negative S prime over S. So negative 22 divided by the object distance, which is 80. And negative cancels out. So what we end up is 0.27. So a positive 0.27. Positive means it's upright. 0.27 means, since it's less than 1, means smaller. Did you expect that to be smaller? Well, remember, concave gives you a virtual smaller image always, right? So they should have expected that. And that means, is the image upright or inverted? You can get it from here, right? So basically, if it's positive, it is upright. Is it real or virtual? It is virtual. And then you can give me 2 reasons for that, right? It's virtual because image position is negative. It's virtual because, it is upright. That means magnification is positive. So those are the 2 reasons that you can use to tell me that the image is virtual. All right, so the last thing we have in this chapter is the human eye. So we're going to kind of briefly talk about that, because the human eye basically behaves like a lens. Because what we have here is there is part of the eye that basically acts like a lens when the light enters your eye, right? And there's then the kind of like a fluid here is a little bit, and that fluid kind of deflects the light a little bit until you have then the retina, right? When the light basically hits the retina, and then the image is generated. So basically kind of like this. So you can see, right? So what you have is that normal eye forms an image on the retina of an object at infinity. So what you have here is then you can kind of think of like this part of the eye is like a lens, okay? And it's kind of like the converging lens like that, because the light then will be converged into your retina, okay? Now, the idea here is in normal eye, where the light is, you're looking at some object, right? Let's say, remember, so this distance here is S prime, where the image will be formed on your retina, right? It's very small, okay? And technically, then any object can be considered really, really far away, and the light will be, more or less parallel. So in a normal, healthy eye, the image will be formed on your retina. That means your eye lens here able to accommodate, that means, bulge a little bit or become thinner, so that image is created on your retina. But then you have the defects of vision is then when your eye lens cannot accommodate. And for example, in this case, you can have what we call myopic, right, or nearsightedness, where the eyeball is the long form is too long from the front to back in comparison with the radius of curvature of the cornea, and rays from an object at infinity are focused in front of the retina. That means what you have here is it bends it too much, right? It bends it too much. That means it converges earlier than it should, instead of converging a little bit further where your retina is, okay? So this is basically the, called myopic or nearsightedness. That means the object, right, appear to be, a blurry, like let's say when you look at it. So this is in terms of, let's say, can be, corrected, not, let's say you can't fix it, but you can correct it by, using a lens, okay? So one thing we have is that the far point of a certain myopic eye is 50 centimeters in front of the eye. So one of the things, let's say we have. So when a diverging lens of focal length f equals negative 48 centimeters is worn 2 centimeters from the eye, that means your, those, reading glasses, right? So let's say if it's, diverging lens, it creates a virtual image at 50 centimeters that permits the wearer to see clearly, okay? Because what it does here is generate a virtual image, right? Because it's a diverging lens that, it can then help you to generate the image on your retina, and then you can see everything, kind of like the sharper. Okay, so that's kind of like the idea for, how to fix the nearsightedness. You use a diverging lens. So, and then you have the farsightedness, right? So when the eye suffers a mismatch between the focusing range of the lens, cornea system, and the length of the eye, with the result that light rays from a near object reach the retina before they converge to form an image. That means this is when you have something really close to you and you can't really see it, in focus, right? So remember, nearsightedness and when you can't see the far, and then the farsightedness is when you can't see the nearby objects. Let's say in sharp. Like let's say it's not sharp; it's kind of blurry for you. Again, this time your eye lens basically is not bulgy enough. It doesn't deflect enough that when it converges seems like at the point behind the retina. So that's why it doesn't seem to be, let's say sharp again, because the image is formed, behind your retina. So that's why what you have here is, this is known as a farsightedness, okay? All right, so a farsighted person can usually see faraway objects clearly, but not nearby objects, where the nearsightedness can see the nearby objects clearly, but not faraway objects. And we can basically correct nearsightedness using the diverging lens, right? Because remember, so the idea here is, so if I kind of go back over here, so remember, so the idea here is this is where the image is located. But if you put the diverging lens, so it kind of diverges light a little bit and then converges, and they then converge at the retina. That means they kind of diverge the light a little bit and then allows it to converge, so which helps you to then have a image on your retina. Okay, but for this one, what you have here is your image is located behind. That means it's not strong enough. That means what you do here is you put another, converging lens right now in front of it, and then it bends it more, because two converging lenses together will bend the light more than if you have just one converging lens, which will bend it somewhere over there. Okay, so that's kind of the idea. So that means you can see, right? So you have a nearby object and images generated somewhere over there. Then what you do, you put a converging lens, which then generates an image of the object further than actually it is, which then allows you to generate the image of that on the retina. Because remember, the farsightedness, we can see further objects better than nearby. So it generates a image of the object that is further, and then we see basically the image of that image, virtual image of the object. That means what you have kind of two things. So your glass generates a virtual image of the object, and then this virtual image of the object is acting like actual object for your eye lens, and it generates image of that. So that's why. And remember, all doesn't matter, your eye lens generates a real image. So you can see, right, always on your retina you have a virtual, you have an inverted real image. Okay, and then actually, that means your retina generates everything around you upside down, and then your brain, right, before, let's say, comprehends everything, have to like turn it over, upright, right, to actually, see everything the way it is. But on your retina, everything is actually upside down. All right, so generally what we do here is for the, for specifically for eye, we use diopters, or, as a unit to represent what we call power of the lens. So the power, nothing but, let's say, 1 over the focal length of our eye lens. So a converging lens of a focal length 120 centimeters is a power of 15 diopters. So let's say when you go by, reading glasses, they might give you in terms of what power do you want? Do you want +3, -3, and things like that, which then kind of like the correcting, like, let's say, how much do you need to, do you need to make it, let's say, thinner or thicker, and so on and so on, like, let's say, what type you have. So you can see, right, focal length of 120 has a power of 15 diopters, and a diverging lens of a focal length of 240 has a power of 22.5 diopters. Okay, so, and what we have here is, so let's say, we have an example here where we have a farsighted person requires a lens that have powers equal to 1.75 diopters to read comfortably from a book that is 25 centimeters from his eye. What is that person near point without the lenses? Okay. So remember, generally, if you are a healthy person, right, this near side, you know, this um, near point is roughly about 25 centimeters. Okay. So, and what we have here is, let's say, if you're considering trying to correct this particular person's, you know, a vision, right? So you want to, you know, assuming that you're given, you know, what type of powers you have, right? So that the power is 1.75 diopters. And we're given the book, which is the object, is 25 centimeters from that, right? So one thing I can do here is, remember, this is can be used, right? The power can be used to find the focal length, because power is equals to 1 over the focal length. That means focal length is 1 over the power. So doing 1 over, you know, 1.75 can then give me the, you know, the focal length of this lens. So 1 over 1.75. So we get 57 centimeters. All right, so we get 57 centimeters. All right. So then if I'm calculating the image distance, 1 over s plus 1 over s prime equals 1 over focal length, then what I can do from here is calculate s prime, which is then s times f divided by s minus f. Okay, so I can calculate this, and once we plug in all the values, right, then one of the things we're going to get here is we're going to get negative 44.4 centimeters. Okay, that means that this is going to be in terms of the near point, right, because the image will be generated at that position. So 44, or you can say that near point is 44.4 centimeters, right? But then the image will be 44.4 centimeters in front of the lens. Okay. All right, so one more example here. A nearsighted person cannot focus clearly on objects that are more distant than 2.25 meters from her eye. What power lenses are required for her to see distant objects clearly? All right, so what we're given here is, again, you know, way of solving for the, you know, let's say power, in this case, power of the lens, right? Remember, power here is equals to 1 over f. That means I need to find basically this focal length of this particular, let's say, you know, eye lens, right? This, you know, for this particular lens. What I have here is we're assuming that the objects that are more distant than 2.2, let's say that person cannot focus clearly on objects that are more distant than 2.25 meters. That means we want to look at in terms of distant objects clearly. Remember, what is a distant object? We assume that distant objects are far away, really far away. That means, you know, for our purpose, we can call them infinitely far away. That means 1 over s plus 1 over s prime equals 1 over f. Well, if this guy here is infinitely far away, then this whole thing is 0. That means s prime is equal to the focal length. Well, since we're assuming that, you know, s prime here is 2.25 meters, right? That means so is the focal length. Then power here is equals to 1 over focal length, or 1 over 2.25 meters. So we get them 0.444 diopters. Okay. Again, because it's a, you know, distant objects, we can always take the distance to that object, really distant object, right, to be infinity. And then the image will be generated at the focal length, right, the focal point. So then we can use that to calculate this. All right, guys, so this concludes chapter 24.